Welcome to the video on diagrams, combined, mutually exclusive, conditional, and independent probabilities. So first we have our Venn and tree diagrams. So a Venn diagram is good if you have a couple of different entities where there are overlapping attributes. So one would represent A. So inside you'd have the probability of A. And in here, which would be B, you'd have the probability of B. And the middle section would be their overlapping parts. So if you had 50 people and you're wondering if they like pizza, tacos, or both, or neither, you could say we have 20 that like both. If we have 30 people that like pizza, that means 10 only like pizza but don't like both, because this part is part of both circles. And then if you had, say, 15 people who only like tacos, then the total number of people that likes tacos would be this whole circle, so 20 plus 15. So that would be 35. So that's when you would use a Venn diagram. A tree diagram is best for calculating probabilities when you have a sequence of probabilities. So if you're flipping a coin, for example, this could be the probability of heads versus tails. And then you would have heads and tails, heads and tails. And if you wanted to know the probability of flipping two heads in a row, you could go to this branch here and multiply those probabilities, because that would be the probability of both being true. So tree diagrams are best for a sequence. Then we have outcome tables. So you can see the entire sample space or a table of the outcomes. So if you're flipping a coin, and you can get heads or tails, and rolling a dice, where you can get 1, 2, 3, 4, 5, or 6, your sample space is this whole area in here. You could get a 1 and a heads, a 1 and a tails, or any of these options in here. For this table here, this would be finding the sum of two dice. So if you rolled both dice and got a 1 on each of them, then your sum would be 2. So this is all of the possible outcomes. So if you want to know the probability of getting a 9, for example, you could see how many 9s there are. There are 4 9s. So it would be 4 out of, and then the number of outcomes is 36. Because that's how many different outcomes there are here. So our probability of getting a 9 would be 1/9. So that's how you use those tables. So for probability, if you have a symbol like this, it means and. So you could find the probability of flipping a head and flipping a tail if you're flipping two coins. If you have the one that looks like a U, that means or. And this or is non-exclusive. So with our Venn diagram, if you wanted the probability of A or B, that would be the total area of this entire thing, not just the probability of just A or just B. So this middle section is included, and that's why it's a non-exclusive or. So if we're doing something where there is replacement, the probabilities don't change each time. But if you're not replacing something, the probabilities will change because things are removed. So if we had a bag, for example, with 3 blue marbles, 2 red, and 1 green, the probability of drawing 2 blues in a row with replacement would be 3 out of our total, which is 6, times 3 out of our total, which is 6. So it would be 1/2 times 1/2, which equals 1/4. But if there's no replacement, so if it's without replacement, the probability of drawing 2 blue would be 3 out of 6 times, now there's only 5 marbles left, so it's out of 5, and only 2 blue are remaining because we already pulled a blue out. So it would be times 2 out of 5. So when we multiply this, we could simplify these to 1 and 3, and then 1 and 1. So this would just become 1/5. So your probabilities are different if you do replace things versus if you don't. So for combined events, the probability of 2 events occurring, the probability of A or B equals our probability of A plus our probability of B minus the probability of A and B. So this makes more sense if you look at a Venn diagram. So we'd have our probability of A, which is this entire circle, plus our probability of B, which is this entire circle. So we've added this middle section twice, and that's why we have to subtract the probability of A and B. So mutually exclusive events are events that don't happen at the same time. Because this middle section is non-existent, A and B is 0, so they would just be two separate events with no overlap. Conditional probability is the probability of something given that something else is true. So this would be the probability of A given B. So our probability of someone ordering pepperoni is going to increase if they're ordering a pizza. So if we know B, it'll impact what A is. So to find this, you would do your probability of A and B over the probability of B. Or you could rearrange that equation to look like this. The probability of A and B equals the probability of A given B times the probability of B. And we'll work on that with one of our IB questions. Finally, we have independent events, where knowing the probability of one doesn't impact our knowledge about the other. So with conditional probability, knowing the second one most of the time will change what our probability is going to be. But for this one here, if they're independent, knowing that someone does something doesn't change the probability of something else. So your probability of flipping a coin and getting heads is not going to change if you know what number you rolled on a dice, because those two events aren't related. They're independent events. So now we have our first IB practice question. It says, Wesley tosses 3 fair coins, heads and tails. A, what's the probability of getting 2 heads and 1 tail? So we can't draw a table because there's 3 different things going on. There's 3 coin tosses. But what we can do is draw a tree. So when you flip the coin one time, you can get heads or tails. They each have a 50% probability, or 1/2. Then you can flip it a second time and get heads or tails. Each of them has a probability of 1/2. And then you'll flip it a third time with that same thing. So heads or tails. So your tree starts to get really complicated pretty quickly because there are so many branches. So this top branch here is heads, heads, heads. The next branch is heads, heads, tails. The third is heads, tails, heads. Your fourth is heads, tails, tails. Then we have tails, heads, heads. Tails, heads, tails. Tails, tails, heads. And tails, tails, tails. So those are all of your possible outcomes. So it says, what's the probability of getting 2 heads and 1 tails? So this one has 2 heads and 1 tails. This one also has 2 heads. This one has 2 heads. And that's it. So each of these branches is going to have the same probability because every outcome was the same. So we have 3 of our total 8 branches. So our probability of getting 2 heads and 1 tails is 3/8. For part B, it says, what's the probability of getting 1 head and 2 tails given that the first toss was heads? So we know that this is true, that it was heads first. So everything on the bottom half of this tree doesn't matter. So this time we want 1 head and 2 tails. So we'll scribble out these arrows. So on the top half of our tree, there's only 1 branch that has 1 heads and 2 tails. So of the 4 branches we have remaining, only 1 of them has 1 heads. So it would be 1/4. So now we have our second IB practice question. It says at a school, 100 kids are asked if they play basketball, volleyball, and or tennis. Of the kids surveyed, 6 play all of the sports, 38 played basketball, 12 played basketball and volleyball, 14 played tennis, 16 played only volleyball, and none played only tennis and one other sport. So for this question, we have 3 different sports with some overlap. So we're going to draw a Venn diagram with 3 circles. So we'll label our circles for each sport. So this is basketball, volleyball, and tennis. So it says, of the kids surveyed, 6 played all of the sports. So we need to find the area of this Venn diagram that overlaps with all 3 of them. So that's right here in the middle, and there's 6 people. Then it says 38 played basketball. So this entire circle is going to have 38 inside of it. Next, we see that 12 played basketball and volleyball. So this part that overlaps between basketball and volleyball should have 12. 6 are in the middle section, so we'll have 6 more in the section between basketball and volleyball. Then we see that 14 played tennis. So the entire tennis circle should have 14. 16 played only volleyball. So only volleyball would be the section of volleyball that doesn't overlap with any of the other ones. So that would be 16 here. And then it said none played only tennis and one other sport. So none played tennis and only basketball, and none played tennis and just volleyball. So now we can fill in our other portions. So this last portion of basketball, the whole circle has to add to 38. So we'll do 38 minus 6 minus 6. So we'll have 26 left in this big section. And then for tennis, we'll have 8 here because 8 plus 6 is 14. So part A says how many played none of the sports. So none of the sports would be our total of 100 people minus however many people played basketball, volleyball, or tennis. So we can add up all of the numbers inside of our Venn diagram. So we'd have 26 plus 6 plus 6 plus 16 plus 8. So that's going to be 62. So we'll do 100 minus 62 to figure out how many played none of the sports, and that would be 38 people. Now we want to know how many students play only basketball. Well, we calculated that already. Only basketball would be our portion of the circle that doesn't overlap with any of the other circles. So that's going to be 26 people. Finally, it says, what's the probability that a student plays volleyball or tennis? So if they're in the volleyball circle or the tennis circle. So we'll add all of those numbers. So we have 16 plus 6 plus 6 plus 8. So that's going to equal 36. 36 out of the total 100. So that's going to be 0.36. That's the probability that a student plays volleyball or tennis. We could also do this with our equation. So our probability of volleyball or tennis equals our probability of volleyball plus our probability of tennis minus our probability of volleyball and tennis. So our probability of volleyball is our total in the volleyball circle. So 16 plus 6 plus 6, which is 28 out of the 100, plus our probability of tennis. So that's our total in the tennis circle, which is 8 plus 6, so 14 out of 100, minus our probability of volleyball and tennis. So that's our section that overlaps between those two circles, which is 6 of the 100 people. So this is 28 plus 14 minus 6, which is 36 over 100, which is the same as our 0.36 up here. So in summary, our upside down U means and our U means or. For combined events, the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. For mutually exclusive events, the probability of A and B is 0. For conditional probability, the probability of A given B equals the probability of A and B over the probability of B, or the equation written in this form. Our independent events are where the probability of A and B equals the probability of A times the probability of B. And then with replacement, your probabilities don't change each time, but without replacement, your probabilities will change because things are removed. And then we learned about our Venn diagram, our tree diagram, and then our sample space diagram or our table of outcomes. That's all for this video. Thank you for watching.